Hello and welcome to the fourth and last session of our Formula Student Aerodynamics and CFD workshop, organized by SimScale and Formula Student Germany. Yes, today, as you know, we will finish our journey through the world of race car aerodynamics and computational fluid dynamics. And again, before we actually start to dive into our today's topic, I would like to make sure that everybody can hear me loud and clearly. You guys know the procedure. There is a button called Raise My Hand, and please click this button in the case you can hear me loud and clearly. Great, I can already see a lot of hands, perfect. And as you know, we also provide as an alternative a toll-free audio service number. And therefore you just have to call one of the numbers you can see right now on your screen and enter the access code 406-946-292 when you're asked for it. All right, perfect. So again, we have a lot of stuff to learn and to discuss, therefore let's start. So today we will focus basically on two things. We will focus on pre-processing, which is the step you need to learn to be able to simulate your own designs and not only the models we provide you with. And we will also talk a little bit about how to make sure when simulating your own car designs the results are correct. And the second part is a case study. And I'm very happy that Nicholas Pfeiffer joined today. And he is really an outstanding example how you can use the resources and content from this workshop to establish a strong and working CFD process within several months. And yes, I'm very happy that Nicholas will share his experience with you and show you how he leveraged the SimScale CFD platform for designing their car. Yes, finally, we will discuss the last homework assignment. And we will again have time for a Q&A. You might notice that we don't have a live demo today. The reason is that our today's homework is basically based on the last week's live demo. However, we will discuss this in detail at the end of this session. In the case you have questions, just write them into the chat. And maybe just, again, two things. First of all, you can still submit your homework, and we are looking forward to get a lot of homework submissions and receive your feedback and see you being successful with our platform. And in the case you need support, please reach out to us using the SimScale forum and the dedicated forum section for Formula Student and Formula SAE. And just to take a final look at our overview, as I mentioned, this session is about the design process, and Nicholas Pfeiffer will join today as a guest speaker and guest expert. All right, but there's someone else also joining today. I'm very happy that my colleague Akram, who is one of our technical account managers and who has a lot of experience in professional motorsports, will join today and talk with you about the pre-processing and CAD model management. Akram, can you hear me?
Hi, Milad. Yes, I can hear you. Let me just share my screen.
I have to make you the presenter 1 second.
Okay, perfect.
No, you're the presenter.
All right, fantastic. So just let me know if you can see my screen.
Yes.
Okay, great. So good morning, good afternoon, good evening, wherever you are around the world. We really appreciate your time and joining us for this webinar. So the last session of the Formula Student CFD. So as Milad mentioned before, I will be the person who is taking over this presentation about pre-processing and preparation of the geometry. So quick overview about me. My name is Akram. I'm a technical account manager at SimScale with aeronautical engineering background and extensive experience working with CAD and CAE generally, mainly in CFD. So the agenda for today, so first of all, we're going to talk about the different type of surfaces. So when you model geometry using a CAD software, there is different approaches from tessellated surface, from NURB surfaces. So we're going to talk about this in the first part. The second part will be CAD problems. So usually when we design, there is a lot of issues that we will face. And these issues will have a direct impact on the simulation that we're going to run later. And in this part, we're going to discover what are these problems. The last part will be the cleanup of the geometry and how we can clean the geometry to make sure that we're going to have a robust mesh and we're going to have a good simulation that we can rely on. All right, so first of all, let's talk about two different things that we usually face when we talk about 3D modeling. So first of all, it's the precise surface. And the second thing, it's the tessellated surface. In the next slides, we're going to discover what is the difference between these two surfaces and what are the advantages and disadvantages of each category of surfaces. So first of all, let's start with the precise surface. The precise surface is the surface that we create using a CAD. So it's a CAD representation of a surface, and it's mainly based on NURB representation to get these surfaces. So we're not going to go deeper into the details, but just to let you know that this surface is modeled using some lines and some splines that we can control the some point to get the representation of this surface. So primarily we have two types of surfaces. So we have regular surfaces and also freeform surfaces. So as I mentioned, so for this precise surface, we have two types. So first of all, we have the regular surface, and here we have some examples of regular surfaces that we usually can find in our geometries, and we will see that later in one complex geometry how these surfaces can be used to represent some models in the geometry. So here we have extruded surface or sphere or also cylinder or ruled surface. So these surfaces are considered as regular surfaces. The next type of surfaces that we can face or we can find when we use the CAD software to model a geometry are the freeform surfaces. And generally, as you can see, there is a large difference on the curvature, also on the shape and the form. So these surfaces are more arbitrary surfaces. So usually when we work on external aerodynamics and when we try to model, for example, the nose of the car or also some parts from the side pod or the chassis, maybe the chassis is more like regular surface, but for external aerodynamic part, we usually use a lot of NURB surfaces to represent the shape of these surfaces. Okay, so here we have an example of, so from the right side we can see the NURB representation, and we can see that this surface, the blue one, is controlled by these blue lines and mainly controlled by the red vertices that we have here. So when we move these vertices, also the geometry will move, and basically we control by a tension over here between these points and the surfaces. Let's not go deeper in the details of this modeling. So now usually when we know that when we use a CAD software, there is some format that we have to export or to use later for the simulation. And basically some of the most common surface formats that we can find with the CAD softwares. We do have, of course, some native formats, but also we have some shared formats like STEP, IGES, BREP. So these formats can be exported from a CAD software with a NURB representation. Now let's jump to the second type of surfaces, and this is completely different type of surfaces. It's called the tessellated surface. It's a surface representation using identical elements. Usually we use triangles to represent the surfaces, and basically in this type of surfaces we get like many elements. We can have like one element up to thousands or millions of elements to represent a geometry. And as you can see here from the side, so instead of using this approach of NURBs and so on and these splines to represent the surface, so here we are using the small elements that are connected to each other, and they will give you this shape. So usually these formats are mainly available in the softwares where it's more for 3D modeling than a CAD software. So other softwares are mainly relying on this approach, but also most of the CAD softwares, if it's not all the CAD softwares, they have the capability to export this type of surfaces. Some formats that we can find with the tessellated surface, for example, it's the STL or the OBJ. And we're going to talk a lot about the STL because it's one of the most important formats that we use in the CFD. And because you can control the tessellation of the surface, you can make it smooth, you can control the tessellation, also you can make sure that later to check the quality of the surface, it's easier to use tessellated surface than, let's say, a precise surface. All right, so I was talking about this point just a few seconds ago, which is the precision or the quality of the surface. So here we have these four examples, and basically from the left side here we have a precise surface, and we can see that the precise surface, we can't really control the quality of the surface because it's based on this, as mentioned before, these NURBS that will give you this shape of the geometry. So you can't really control the the quality of the surface because it's defined by the software. But going to the next, talking about the next surface representation, which is the tessellated surface, we can see that there is an option to control the quality of the surface by controlling. There is a couple of parameters, but here we are controlling one parameter, which is the number of surface faces or the number of triangles that we are using to control this surface. We can see that with the same diameter, which is 10 millimeter, but the shape it's completely different, and we can get really good quality surface tessellation or surface quality by using high number of triangles. Of course, this will have also some impacts on the size of the file that you will extract later, but to get good quality surface, you have to make sure that you will get higher number of elements to represent the good quality surface. Now talking about the STL, and why we are talking precisely about the STL, because as I mentioned before, STL is a really important format that you will face every day when you are working in CFD. So basically here we are talking about the formulation of the STL file. So the STL file usually will start with a solid, as you can see here, and you name the solid, then you will end with end solid, and you name the solid. And in between the start and the end, we're going to have this, so we're going to represent the surface or the element or the triangles by four things. So we need 3 points because it's triangle, and of course it's a 3D representation, so we need the X, Y, Z coordinate of the 3 vertices, but also another important thing, which is the facet normal. And as you can see here, so we start with the normal in the IGK directions, or X, Y, Z, and also the vertices coordinates in the 3 directions for the 3 vertices. And this is how you formulate your CAD model or your tessellation STL file. And of course, if you have multiple solids that you want to, if you want, for example, a multiple STL file with multiple solids, of course, when you end this solid here, you will open a new one as a solid name, and you name it, for example, here we are talking, for example, about a Formula Student car, so we can name this as chassis, and then the next one will be solid, for example, tire, and we're going to start putting this coordinate for the three components of the triangle and the normals. I hope it's clear. So here we are talking about the conversion of the file. So because, as I mentioned before, most of the software or most of the CAD softwares, if it's not all of them, they are using precise surfaces to represent the geometry. But basically, later when you decide to go for simulation, it's recommended to use an STL file so you can control the tessellation of your surface to make sure that you have a smooth surface. So basically, to convert from a format to another or from a representation to another, there is some things that you have to take in consideration. So to convert from precise surface to a tessellated surface, yes, this is possible. So any software can do this and can convert from precise surface to an STL file or tessellated file. But the reverse, it's not possible. So if you have a tessellated surface and you want to go back to precise surface, this is not possible, and you have to keep this in mind, because if you will decide to do this, what will happen is each triangle from this tessellation will be considered as a separate surface, and you will end up with thousands, if it's not millions, of surfaces that you have to deal with, and it's not the right decision. So always keep in mind, you can move from precise surface to tessellated surface, but moving from tessellated surface to precise surface, it's not possible. And here we have like some formats. So we can go from IGES, STP, Parasolid, or CATIA V5, all these formats. You can take it to STL or OBJ, but you can't take an OBJ or STL to other formats. Okay, so now let's talk about the advantages and disadvantages of an STL file. As I mentioned, we really use the tessellated surfaces a lot when we are working with simulation, especially with CFD. But of course, everything in this world has some advantages and disadvantages. So talking about the advantages of the STL file. So first of all, no convention error, convergence error. Also the high flexibility, as mentioned before, so you can control the tessellation, the chord length, the angle of distraction. So there is a lot of things that you can control with the STL that you can't do with a precise surface. Also suitable for automation. Some disadvantages that we're going to talk about here, it's you will lose the topological information, which is sometimes really difficult to work with in simulation without having the topological informations. Restriction, editability, because you can't edit this model. So as soon as you get an STL file, you can't really edit it. Only if you are using some morphing approach to like stretch the model, this is possible, but it's not really recommended. So the next step, now we're going to talk about the CAD problems. So why do surfaces need to be prepared? So as mentioned before, we prepare a CAD model, then we jump to the simulation, but we'll find a lot of issues. So here in this part, we're going to talk about what are the main issues that we have to focus on when we model a CAD for simulation. So imported CAD model has too many details. This is one of the most problems that majority of people are facing. Possible surface errors can be volume is not closed, surface discontinuity, or surface intersect each other. We're going to see this in the next few slides. So here we have three major problems that maybe all of us, I mean, as soon as you work in the field of SAE, you're going to face one of these problems. And this happens when you create the CAD model, and sometimes when you try to trim a surface, two surfaces, sometimes the surface is not trimmed, or you forget to trim the two surfaces. So what's happening, you're going to have an intersection. And this is one of the common issues that we are facing a lot when we work with the CAD and we prepare a model for simulation. So we have to make sure that our model will be clean without intersection. Also one other thing, which is open volume, because a volume should be like closed volume. And if there is an open or a gap or hole in the volume, this will create issues that later when you create the mesh, you will have cells that will escape inside your model, and this will create problems. So we have to make sure that your model is watertight and without any open volumes, otherwise it's not considered as volume, but it's considered as surface, and you have to make sure that you will close these holes. Another thing, which is the discontinuity. Discontinuity, usually we face this discontinuity when we have two surfaces and we want to connect the two surfaces, and sometimes because of some issues with the CAD software, or maybe just an estimation from the user, so he will not connect the two surfaces, and as you can see, you have this gap, and this will create an issue for the solver later, or for the mesher later, because there is a gap. So this and these surfaces are considered as zero thickness. So the mesh will find some problems, because you will have a mesh from this side and also from the bottom, and then you will have really problems with the simulation later, because you're going to have like cells that are touching each other, but also there is a surface in between, so it's not the right thing to do. So always make sure that you verify your model, that you are free from these three major, of course there is other problems, but these are the three major issues that we are facing: intersection, open volume, and discontinuity. Here we're going to talk about real geometry, and I think most of you are mainly interested about this. It's talking about real life example, and in this example we're going to take a Formula Student car. So basically from here, when we look at this slide, we can see two cars. Most of us, I mean, they think that they are identical cars with the same shape, almost the same, but if you dig deeper into the details of this geometry, we can find that there is a huge difference between the two geometries, and we're going to discover this in a few seconds. But just to give you an idea, so here from the left side we are looking to a construction model or a design model, but from the left side it's construction model, but from the right side it's a CFD, or let's call it CAE, computer aided engineering model. So we zoom deeper in the front wing, close to the front wing, and let's discover what is the difference between a construction model and CFD model. So if you take a close look to this, let's call it this front wing pillars here, or wherever you want to call it, we can see for the construction model we have a lot of details of really the real geometry is represented in the construction model. But if we go to the CFD model, we don't need all these details, because all these details will create a lot of problems later when you try to create the mesh, especially the boundary layers. You will have bed cells, and these bed cells will have a direct impact on the simulation convergence that Milad will talk about it later. So we have to make sure that we clean the model. Of course, you're going to ask me, do you think that this will have an effect on the flow? Yes, that's right, especially close to the boundary layer, but this effect is not really significant. So it's better to have a clean model with a convergent simulation better than having a detailed model, and you will spend a lot of time trying to figure out how to make the simulation works, but then you will not be able because you have a lot of bed cells. So we have to make sure that the mesh is clean, or the geometry is clean to get clean mesh. Also, other details here, these holes that we will use to like change the angle of the flap. As you can see, we have 3 holes or 4, so we have to take off all these holes to make sure that we're not going to have cells here, because these holes, you will have some cells there, and you have to refine. This will add more cells, the number of cells, but also more bed cells that we are trying to avoid. Let's go to another view for the front wing, for the front tires and the suspension, and here you can see a significant difference between the two models, because here we are trying to simulate the real system of the suspension, and we are using all these wishbones, all the system of connection between the wishbones and the let's say the chassis or the nose of the car, also this suspension system. But as you can see, for simulation, we are modeling the geometry with the simplified shapes. As mentioned before, we are using here just a cylinder to represent all this mechanism. Of course, this will have a small detail in the accuracy of the results, but this will not have more than 1% of the total accuracy. So it's really good to clean up, to reduce, or with other words, to defeature the model and make sure that we're going to have clean, watertight, free of error model, to make sure that our mesh will be robust and the simulation will not diverge, and we're going to have like accurate results. Okay, so one really important thing here that I think it's one of the most important things that we have to discuss here, it's radiators. Because a radiator is like, it's a geometry that is built by a lot of small features and a lot of, let's say, shell elements, and as you can see, it's a lot of elements that we can't really simulate, and if we try to create a mesh over this, we're going to have millions of bed cells. So we have to make sure that we're going to model it with just simple geometry, and then there is another approach, and I believe you have already discovered this, which is the porous medium instead of using the real geometry of a radiator. So it's a simplification. going to the back of the car, we can see the same things from the front. So we have reduced we have defeatured the model, and we have reduced the details of the model to make sure that we're going to have a clean geometry that will allow that to get clean mesh without errors, free of problems, that will ensure a good quality simulation for us. And as you can see, I mean, if you just look closer to the suspension system, there is a huge difference. Here's just a cylinder, but here we have all the elements. Okay, so also one important thing when you work with the CAD and you prepare your geometry. So we have discovered what are the different surfaces or models that you can use to model a surface. We have talked about defeaturing the model. And the last thing, so when you make sure that you have a clean model, the next step will be to group your model or your parts into groups that will help you later to do a good pre-processing. So you will apply the refinements that you want in the right position, but also later for the post-processing, so you can post-process your results based on the separate parts, but they have connection. So for example, here we have the red part, which is the rear wing. So the part, it's multi-solids, as you can see. So we have 4 flaps and also the end plate. So it's 5 solids, and we collect all the solids in one part that we call the rear wing. So later when we want to do the pre-processing or the post-processing, or let's start with the pre-processing. So I want to select like a refinement or a boundary layer height for all these elements with the same height. So it will be easier for me just by one click. But if I'm gonna have all these parts are separated apart and I want to do the post-processing, then I have to click on each one, and also for the post-processing later, it's not the right decision. So it's better to collect all the parts that have relation to each other to one solid that will help you in the pre-processing, but also in the post-processing and in setting up the simulation, because you will reduce the number of touch with the geometry. All right, guys, I hope that was helpful for you to discover the basics of different surfaces, the different models that we are using to represent our surfaces, and also what you have to do when you have really complex geometry, what you are supposed to do to clean it, what parts you have to focus on to reduce, and also the last part, it was about collecting the different solids in one part, so this will help you to reduce the work for you and to get more control over your geometry in the pre-processing stage and also the post-processing stage. So it was a pleasure to the guys to present this for you, and now I'm going to hand it over to my colleague Milad.
Akram, thank you very much for this outstanding presentation. And before you leave, I know your time is precious and you have some other stuff to do today. We have some questions. I've just chosen this 3 questions regarding model processing, and I hope that you maybe can help our participants and students to get it right. So,
of course, with pleasure.
The first question is by Thomas, and I know this name. He was taking part in a lot of webinars this year. Good guy. And his question is, tessellation of a long cylinder will most likely produce a high aspect ratio triangles. Can that translate into an issue in the CFD mesh?
I'm going to say not really for CFD, especially if I know what he's talking about here. So the aspect ratio will be the length of the triangle and also the width of it. So there is a really large aspect ratio. It's better to have low aspect ratio, so also you can control it by reducing the maximum height of the triangle. This will help you to get better tessellation, but I'm going to say this will not have an effect. So you can work directly with high aspect ratio for the cylinder, but I suggest it's better to get more identical triangles with let's say the 3 arms of the triangle with the same dimensions.
Perfect. Absolutely right. And then the next question by Tushar Goyal, and he wants to know what is a topological information.
Okay, so basically for the topological information, so it's when maybe Milad, you can give an information about this.
Yeah, for sure.
Yeah.
I think it was basically also mentioned by Akram. When talking about topological informations, and I don't want to go too much into detail, we are talking about the fact that if we, for example, use a precise model, it's possible, for example, if you have a cylinder, you can just change the radius of the cylinder and everything else will change. But when we talk about tessellated files, we don't have any more the topological information, which means that we can basically not edit it very easily. So this topological information, it's about how or if we can still edit the model. And that's a big difference. It's quite easy to modify a step file, but it can be horrible to modify a STL file because it can mean in the worst case you have to rebuild the full model from scratch. And that's a big difference. But really you should focus more on the information Akram talked most about, like cleaning up the model and use the STL file format. I hope that answered your question, Tushar. The next question is by Dietrich. And his question is related to geometry cleaning. He wants to know why did you remove the leading edge just right behind the front wheel at the under tray, and why did you combine the flaps at the under tray? Those two wings have an impact on the flow behavior, and the gap between the flaps has also a big impact.
Let's just jump back to it. So the front wing, and what is the part that he was asking about?
Yeah, I think one thing which can be a little bit confusing, actually this is not exactly the same car. There are different stages of the car. So if a wing disappeared, a main wing, this can also be related to the fact that it's a little bit different geometry if you take a look. But I mean, I don't see that there was something removed, honestly. Dietrich, maybe you can specify your question more, but...
Or also maybe because of the view, because it's not the same view, so you can see it's like the perspective, it's not the same, so maybe it's just visual effect, but yeah. I can see that we have the same, so we have we have flap, the main wing here. I mean, the major parts are secured, so we have the same major part, the front wing with the main wing, the flap, the end plates, but what we have changed it. So if you just take a close look here, we have changed this. We have closed these holes that we use to control the angle of attack, and also some parts here of the assembly. So these parts will not help us a lot to create a good quality mesh. Talking about the rear wing, I mean, we don't have a picture for the rear wing, but here.
Akram, he's talking about the previous slide. About the bonnets which were removed, and this whole different structure of the side wing. Go one slide back. Oh, this slide, exactly this. Wait,
this one.
1 second. No, one slide back. One slide back. This one. And
okay.
The reason, Dietrich, is that basically these are two different cars. This is the car of the previous year on the left side, but we only had the clean model for the last year's car, and that's the reason why the cars are slightly different. So, for example, this wing on the side pod, you can see it. It was not a simplification that we merged it. It was just a different geometry. I hope that was not too confusing, but it was not simplification. This difference between, for example, the side pod. It's because of the other geometry. And if you take a close look also at the front wing and at the rear wing, you will see that it's a little bit different model structure. However,
yeah, that's right.
Tusha wants to know something about vortex generators, and his question is that they are basically quite small, and if this also means that they also should feature vortex generators.
Basically, vortex generators are so small to get to be on the same level of the boundary layer, and we can't really. I mean, I don't suggest to defeature the vortex generator, but what I suggest is to create really high quality mesh over the vortex generators, so you will really get the right shape of it, so you can predict what this vortex generator will do on the boundary layer. Because if you are defeature it, you're gonna this will have a huge effect on the performance. What I suggest is to keep the vortex generator and increase the mesh close to the vortex generator to make sure that you're gonna get good representation of it and good prediction of the physical behavior of the vortex generator on what the vortex generator will do for you. So don't defeature the vortex generator. Defeature only the things that have more mechanical rule in the geometry.
All right, thank you very much. We have some more questions, but we will answer them at the Q&A. Akram, thank you very much for joining today.
Thank you. It was a pleasure for me, and have a nice evening, everybody. Bye-bye.
Bye. All right, good to be back. And now let's talk very quickly about ensuring result quality. And the reason why I want to talk with you about that is that, as I mentioned, the idea of this session is that you will be able to take the knowledge you've gained during the last 3 weeks and adapt it on your own car design and design process. And basically, the great thing is that you can really start with a mesh setup and the simulation setup reused for this workshop, and you can just adapt it and improve it step by step and really adapt it to your needs. And the very first thing I want to talk about is basically the accuracy of CFD results. And right now on the slide, you can see a simulation case of external aerodynamics of a motorbike. And basically, what I did is that I wrote out the simulation results for every iteration of the simulation, and this animation clearly shows how the result is developing. So at the beginning, the result is quite unphysical, and with time it becomes more accurate and accurate. And that's the very first important lesson. You cannot use the number, you need to adapt the number of iterations. You cannot just use the settings we provided you with, because the right number of iteration depends mainly on the simulation. And you should stop your simulation once you have reached convergence. And here you can see that starting from 2,000 iterations or maybe 1,500 iterations, the result is not changing anymore. It's more fluctuating. And that's the point where we want to have our results all the time. And so let's talk about the 3 dimensions of convergence. The very first dimension is what we call residual. And I think I showed you this plot several times. You can also see it on the platform. And basically here we are just plotting the error in the solution of our system of equations. And basically this chart is representing for every iteration the maximum or average error for calculation of ux, uy, uz for the velocity, basically for the pressure, for the continuity, and for k and omega. And this one is very important, because once this is converged, it means that you don't have a big global change in your simulation result. But it doesn't necessarily say simulation result is right. It just says that from a numerical point of view, your problem is converged. The next thing you should take a look at is a force plot. And we showed you how to create force plots. And basically, you should not consider your simulation as converged if it's only the residuals which are converged. Also the forces need to become constant. The only difference is at the residuals you want them to become as small as possible. For the force coefficients you just want them to become stable. And if you take a look at this and you just imagine, basically the forces were predicted completely wrong until 20 iterations. Then it was let's say the same right magnitude but still fluctuating, and starting from around 50 iterations becomes stable. And here you can see what happened. At this 50 iterations the convergence plot jumped, which means that here something very important happened, and before this point the simulation is just a colorful picture. And the third dimension you can use to make sure your result is converged is to take a look at a single point. So for example, just choose a probe in the near of the car and plot how the, for example, pressure of this probe or velocity is changing. And that's really great, because on the right side, using a probe, is really focusing on one certain point. The residuals are focusing on the whole result, and the force plots only on the surfaces. And these three tools together allow you to precisely judge if your simulation setup is converging or not. One aspect which is very important for this is mesh quality, because just imagine you will use our setup exactly for your model. You will use the same boundary conditions, same numerical settings, same number of iterations, but it can happen that some result is not converged. And one reason is the mesh. As you know, the mesh is discretizing our problem and dividing it into small subvolumes. And a mesh has something what we call a quality. And basically it's about to be able, or basically mesh quality is about to compare a perfect mesh with our actual mesh. And a perfect mesh, it would mean it would be made of 100% regular elements. And SimScale comes with some quite powerful logs which help you to understand and improve your mesh quality. So let's take a look at this. On the left side, you can screenshot from the SimScale platform from our last week's model, and just on this meshing tree of our mesh operation, on the bottom there is this field or this bottom meshing log. And if you click here, you can take a look at the log output file of our mesher. And if you scroll down till the end, you will see this final section. And here, all information regarding our mesh are summarized. So first of all, at the top, we have a summary of the layer mesh. And here you can exactly see how much, which surface mesh parts were extruded to layers, how thick the layer is overall, and which percentage of the surface is covered by layers. And a lot of times, for example, when your mesh quality, what we'll talk about at the next slide, drop, one reason is, for example, that layer mesh generation is failing. And then you can just check here, and if somewhere it's really much below 70%, you should take a look at the CAD model of the surface. The next thing is, if you go below to other information boxes, here you will receive all information about your mesh size and distribution. So these are the total numbers of cells with a size of 0, total number of cells with a size of 1, and so on. And this gives you a quite good overview over the total mesh size, about the distribution of different refinement cell levels, and also about the time needed to write and create the mesh. To save it. Then we have two other tabs below about the mesh quality. One is summarizing the mesh quality with CFD related metrics, and the other one is expressing the mesh quality with general metrics. And let's just take each of these criteria is tested by the software, and it gives you how many cells are over your quality criteria. For example, for non-orthogonality, it's at the angles it's between 75%, and we have 48 elements which are higher with a higher non-orthogonality. So let's another two key metrics I would like to introduce is the aspect ratio and the skew. And now let's talk about in detail what they are looking like. So we have the orthogonality, and it's basically representing how the interface between two cells is orientated. And if you think about it, this is very important, like for numerically interpolating and calculating fluxes, gradients, etc. And in the best case, it's looking like this. So we have not an angle between the normals of the shared interface. That's a very important point. So let me take my pen. We have here a normal, and here the two normals are in the same direction. But here we have one normal here, and the cell orientation is here. So this is our angle. And this angle should be 0. And as smaller this angle is, it's much better for the mesh. Aspect ratio is a little bit different. It's basically also used for the CFD meshes and a lot of other geometrical properties. An aspect ratio is basically, yes, as the name says, the difference between, the magnitude of the length and the height scale, for example. And the aspect ratio should be as close as possible to 1. 1 would mean you have a perfect element. And here, for example, you have an aspect ratio of 16 because it's 16 times larger than its height. And this is really also something important, and you should try to reduce the aspect ratio as much as possible. And the last thing is skewness. In contrast to orthogonality, skewness is about not the angle between the elements, the interface of two elements, but about the angle between the surrounding surfaces of a single element. And here again, the best skewness is displayed on the top. It would refer to 0, and as larger the skewness is, as worse is it for the mesh quality. Okay, I talked a lot of times. Now I see we have some more questions I will answer, and then we will start with the presentation of Niklas. Okay, let's just choose 2 or 3 questions. Thomas wants to know if it's possible to visualize orthogonality, aspect ratio, and skewness of the car model in the post-processing for visual evaluation. Thomas, right now this feature is not available, but it's planned and I'm quite sure it will be implemented soon. All right, and I see you have some other questions. Let's answer them all at the end. And now I'm very happy to give the word to Niklas Pfeiffer. Niklas, can you hear me? Let me just unmute you. Niklas?
Can you hear me?
Yeah, we can hear you perfectly. I will just make you the presenter.
Yeah, perfect. Perfect.
And now you should be able to share your screen.
Yeah. Can you see my screen?
Yeah, we can see your screen.
I need this screen, I think. Do you see the arrow picture?
No, you need the other screen. You see your background image right now.
Yeah, that's right.
Okay, perfect.
So now you should see the presentation,
yes,
right?
Yes, everything is working.
Perfect. Okay, yeah. First of all, thank you for giving me the opportunity to give something back for the nice collaboration over the last season. I'm really proud to present you a bit of our last year's work, and I hope I can help all you that are the participants to get familiar with CFD and with Formula Student Aerodynamics. So I think Milad already introduced me to you. I'm Niklas Pfeiffer. I'm the head of Aerodynamics from the eMotorsports Cologne Formula Student Team from the Technical University in Cologne. I'm still 19 years old for a couple of days, and I'm in the team since October 2015, which means that I'm now looking forward to my 3rd season already. And yeah, I was in the same position as you guys last year were. I was a participant of the SimScale workshop, and yeah, it was really great, I think, and I got a lot from that. And yeah, so let's start now. I have 2 main topics for you today. The first topic is something I call from cut to cut, which is something like the process from the CFD model, which Akram showed you, to the construction model. And I will show you all the steps that are in between those steps. So, and what would be a better example for that than our plate in front of the rear tire? It was an update before the Formula Student Spain, and in Spain I had to answer nearly every day the question, why do you have that big plate on your car? And yeah, I just thought this might be the perfect example because I will show you what this plate is doing. So the first big thing is that CFD begins with organization. I don't like that topic as well, but it's essential for not losing the overview of all your simulations. And yeah, it starts with setting up a name standard for your geometries. In our case, we do it like we have first the velocity in which we simulate the geometry. I will say more on that later. Then we have the date on which we created the geometry. We have the number because sometimes it happens that we simulate more than one geometry per day. and we have the name of the team member who created this geometry. And as an example, you have for a simulation which was at 60 meters per second. It's called 16 meters per second 2017, October 12th, V1 from NIPFE, which is something we call construction initials. The NI stands for Niklas and the PFE for Pfeiffer. So I hope you get it. And please make sure that you documentate all changes that have been made before setting up the simulation. This is really an important point because over the season you will do a lot of simulations, and if you lose the overview over these simulations and you don't know what you simulated and what has been changed, then you will lose so much time. And therefore I will recommend you to set up something like a data sheet for each simulation in which the informations of the simulations are in. So you can see the most important part is the top box, which is called background information. There's just the date, the short name, the name of the actual status quo geometry, and the name of the new geometry name. And the most important point is the differences between base geo and new geo. In this case, you can see that we changed the plate height from 50 to 250 millimeters, and those are things I don't know 2 months later. So we documented it, and also if you can show these things in the engineering design report, then it will give you some extra point, because that's what engineering is all about. So as Akrem already said, the most common file format for the SimScale platform is the STL file format, and make sure that you rename the STL surfaces after exporting them from CAD, because if you export them from the CAD system, then they have some kind of cryptic names, and if you want to rapidly set up a simulation, then you just have to don't know which surface is from which part, and just invest that time and rename all surfaces. But make sure you don't only rename the files, also rename the surfaces itself. So if you right click on a surface and click open with, and open it with the text program like editor or Notepad++, then you can just change the name. It's the thing that stands behind the solid. It's on the first row of the file, and it's on the last row of the file. I think Akrem told this already to you, so I will go into detail here. So the next thing is, now that we have all the surfaces renamed, we have many different surfaces, but they are not in one file, and therefore SimScale provided us with an STL merging script, which exactly does what its name says. It merges STL files, and it's very simple but very cool tool. And it will be available with this week's homework assignment. So what this thing is actually doing, you just right click it, set run, and yeah, then it merges all the files that are in the folder to one single file. And then after you merge the STL, you can compress the file, and then you can upload it to the SimScale platform, and then it's kind of tidy. So that to the organizational aspect. Now let's move on to a bit more technical and aerodynamical aspect. And yeah, I just want to say that downforce is the force. This is often forgotten. And as I think René and Torbjörn told you already, a car moving through air causes forces, and those forces act on the suspension system and on the tires. And when a Formula student car is moving through the air, then in most of the times it has a very big vertical component, which we call downforce, which presses the car onto the ground. And yeah, due to that force that is acting on the car, the ride height changes with velocity. And yeah, I want to thank the Aero Django's from the Too Fast Racing team from Munich for giving me the video and to show you how this looks like in reality. So as you can see, you might orientate on the ZF logo on the front wing. So now the speed is increasing and the car gets closer to the ground. And now as the speed decreases, the car gets up once again. So this is a pretty nice example for that. Maybe we can have a look at it once again. It's just so impressive, I think. Look how the logo is just hiding behind the front tire. It's really awesome. Well done, guys. So this has, as you might imagine, a very big effect on your CFD simulations and on your results. And therefore, I recommend you to design your CAD model parametric. And there are two ways of doing this, and I will show you them and show you which one is better for myself. And here you can see that we designed the tires not fixed to a position, they are moving. So you can see that on the left-hand side, the tires are touching the ground. On the right-hand side, there is a big space between the ground and the CAD model and the tire. And on the SimScale platform, if you upload this geometry and you set the background box point up, so you keep the ground up, then you reduce the ride height of the car, and the effects of this ride height change were covered. But there's one thing that comes with this method, and that is that you have to change the minimum Z value and all the tire midpoints all the time if you simulate at a new velocity. And therefore, I will show you another method of doing this parametric and of giving you the relative motion between the chassis and the ground. And this is by just mounting the tires fixed to the ground and moving all the aero parts and the chassis and the radiators and so on. It's a bit more work in the beginning when you design the CAD parametric, but in the end you have less work to do because you don't have to change the floor value and the tire midpoints on each simulation. But independent from how you do it, make sure you do one of those two, because if you just simulate in your static CAD setup, then your car will have a totally different behavior than it has in the CFD. So make sure you cover these effects. So now that we have perfectly prepared our car, we can start to set up the mesh and the solving. But I don't want to go into detail here because I think that is what the previous 3 sessions were all about. And if you couldn't make it to one of those sessions or just want to get some solutions, just visit simscale.com/FSAE. And on this site you find all the homework assignments and tutorials and also the recordings even from this session. One thing to the solving of the simulations, in the tutorials that you made in the last sessions, you simulated with a speed of 20 meters per second. In my opinion, that is a bit high for Formula Student purposes, because I think the normal velocity on a Formula Student track is something like 60 kph. So we are simulating with 16 meter per second all the time, which is something like 57.6 kph, I think. And I think that fits way better than the 72 kph that are used by SimScale. But it's not wrong. But I just think that the car is more often operating at 60 kph. So after the solving comes the post-processing, and the post-processing really is the most important part of CFD, because in the post-processing that's why you're doing CFD, because you want to do because you want to know what does a geometry change made for an effect for the whole car. And the post-processing is very, very time consuming, and it takes a lot of time. But therefore we are working towards an automatization of this, which is called process automatization. And yeah, SimScale provided us with some great tools I will show you therefore, and we even programmed ourselves some tools to make post-processing more time efficient and to do more automatically. So we still have to do very much manually, but at some points we just have to click run and the computer works for us, and that is where we want to go with everything. So the first type of post-processing is the numerical post-processing, which is something like an analysis of the forces which you get from the result control. And we have programmed ourselves a little Excel tool, which I want to show you now, which makes this very, very easy. So I hope it opens. Let's see. Yeah, I think it's open. So actually what we have here is we have an input section, which is this section over here, where you just type in all the forces that you get from the geometry, or that you get from the CFD simulation on SimScale platform, and you compare them to the actual status quo of the development. So in our terms, with the plate, the base geometry is the car without the plate in front of the rear tire, and the new geometry is the car with the plate before the rear tire. And as you can see, we typed in here all the forces that we got and the balance, and what we get is a completely automated analysis of those values. So you can see the differences in lift and the differences in drag and the differences in efficiency here, as well as how we met our self-defined target balance, and it even can say if an improvement in performance is expected or not. So let me just show you this. If our under tray, for example, does lift and not downforce, I will just kill the minus here, then you can see everything is changing. So we have decreased downforce, we have decreased efficiency, and an improvement in performance is not expected, which will be something like the change didn't make any sense, and we will put this part on the car. So this tool is, I think you can program it very, very simple by yourself. And yeah, I recommend you to do that because it makes the analysis a lot easier. And another great thing that comes with this tool is you can save this for each individual simulation, and afterwards, together with the data sheet of the simulation, you have a very big folder for the design presentation in which everything you simulated is perfectly documented. So that will give you very, 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 very good points in the engineering design, because you can say, hey, in December I did this simulation, we changed that, and it doesn't have an effect, and then the judge sees this and says, okay, yeah, so the version you have on the car is the best one you could reach over the season. So make sure you do something in terms of numerical analysis. So now that we know what changed in terms of forces. We could just say, okay, it's aerodynamically better, let's mount it to the car, but that's not good engineering. And we won't do that because we don't know why did the changes happen. And for the engineering design presentation, you definitively have to know why it is better than the other version. And this is the point where visual post-processing comes into the game. Visual post-processing, that's for myself, I really like that because it makes something visible. And in terms of aerodynamics, it is very amazing if you can see something. I don't know if you, when you're watching Formula One, and sometimes it happens that you see a front wing vortex or a rear wing vortex, and that's something I really like. And yes, CFD could make it a bit visible what is happening there, and that's why I really like the visual post-processing. For example, here on the left-hand side you can see the foot plate vortex of our front wing, and on the right side you can just see the pressure distribution over the car. So the generating of those plots takes a lot of time, and it really is very, very time intensive to do all those slices manually. And yeah, but as I said before, some things don't have to be done manually anymore in our team, and this is one of those things, because SimScale provided us with a very, very nice script which automatically generates sectional views of your result file, and this makes us able to generate animations like this one, and yeah, without spending much time to generate it. As you imagine, if you do every single of these slices on the platform, it will cost you days, but we just click run, and then yeah, it automatically generates the slices, and yeah, that tool is pretty awesome. And afterwards you have a big folder of CFD pictures which you can look at, and in which you can see very, very much things. And yeah, the nice thing is the script will be available for all sponsored teams after the workshop. So you will get the script from SimScale, and the only thing you need for that is ParaView, which is the post-processing software, but it's an open source program, so you can just download it free. And I recommend you to use Notepad++, because setting up the script is much easier than doing it with the editor. So, but now let's move on to the visual analysis of our plate. The forces set us that we increased the downforce of the undertray, but made it less efficient. And you can see why in the next slices. So first of all, have a look at the area before the plate on the undertray. On the left-hand side, you see the plate is mounted to the car. On the right-hand side, you can see it's not mounted on the car. And what you see on the left-hand side is that there is a big region of high pressure on the undertray, which pushes the undertray down. And on the right-hand side, you don't have that area. So there is an improvement in downforce due to the pressure difference from top to the bottom. And as well, this plate works as a massive gurney, and even on the lower side of the undertray, we have a higher suction effect. And yeah, that is pretty cool, I think. Another pretty cool thing is, if you look to the tires, on the left-hand side, you can see that the tire only has a region of high pressure only on the edge of the tire, on the outside edge. And when you look on the right-hand side, where the plate isn't, there the rear tire is fully in the wind, and the air hits the tire frontally, and yeah, this causes a lot of drag, and the drag of the tires is even reduced by the plate. So it's pretty simple, pretty effective, but yeah, I think rather ugly. The last thing we mentioned was that the efficiency of the under tray was decreased, and you can see that perfectly if you compare the total pressure plots of the car. On top you can see the version without the plate, and on the bottom you can see the version with the plate. And as you can see behind the plate, there's a very big region of low kinetic energy air, and where the air is blue, you are losing some energy, and you are losing a lot of energy here, and this is why the efficiency of the under tray is going down. It produces more downforce, but it produces also more drag. But as we saw in our force analysis before, the overall downforce and the overall efficiency of the car was increased due to the plate. So it's only the under tray which is less efficient, and that is something which we can live with. So afterwards, but now let's move on to the lap time simulation. At this point, we know that we achieve better aerodynamic behavior of the car, and we also know why it is better. The last thing we need to know now is, before we mount the part to our car, if it is really making our car faster, because the plates itself, they have a weight, and it could be that the additional weight you get from the plates makes your car slower than the improvement in downforce makes your car. So therefore, every part of the aerodynamics team has to prove its worth to the performance of the car with a simple lap time simulation. This tool we used in the last season is called Optimum Lap, and it's available free. It has some rather big limitations, and that is why we are developing our own lap time simulation in the moment with MATLAB and Simulink. And in it there will be things like aero mapping, which can't be included in the Optimum Lap simulation. Yeah, but we're working on it, and yeah, we definitely want to improve there. But to get an overview, if something is good, or if something improves your performance, the Optimum Lap simulation is quite good enough. So what we did here, you can see we typed in on the left hand side all the data for the car without the plate. So we had a mass with the driver, and we typed in the drag coefficient and the downforce coefficient, which is the CL. And on the right hand side we did the same for the setup with the plate. So as you can see, we are around 500 grams heavier than before, but on the other hand side we now have an improvement in the downforce coefficient and only a very small improvement in the drag coefficient. So the lap time simulation now simulates the track in Hockenheim and how a perfect driver would drive on that track. And it gets you something like a table in which you can see many different values, and the value that interests us the most is the lap time, of course. And what you can see here is that at the end of the day, the plate gives us an improvement of around 0.23 seconds per lap improvement. So this is how we do from CFD to the CAD model, and I hope you got a small overview. I think it's right. It's quite a big topic to present in such a short time. And of course, if you have any questions, you can just type them in the chat box, or you can send them to me per email later. But I will go on to that later. So now to finish my presentations, I just want to give you some tips, tricks, and guidelines. yeah, just with the experiences we made over the last season. And the first thing, therefore, is how do I start developing? That was something which which was really hard at the beginning of the last season, and I recommend you to have a look at those two books. On the one hand side, Rennwagentechnik. I think everyone in the Formula student knows that book, but that has a reason. And in this book is a guidance for a manual calculation of the wing package, and that is a very, very good good starting point for your development. You can just manually calculate the wings, and then you see that there are some limitations and that you have to do a bit for your own, but to get started it's very good. And on the other hand side, we have the book Competition Car Aerodynamics, which is in my opinion one of the best aerodynamics books, because it is very well written, and the author of the book has many examples of the real life world to show you what aerodynamic devices do, or to show you complex aerodynamic things. And yeah, it's a very good to read book. There are some things about formulas and so on. It's not that 100% formal, but you can get a lot of understanding from that book. So another thing I really recommend you to do is keep in touch with your suspension team, because the communication with your suspension department is essential for designing your aero package, because they have a lot of data which influence the aerodynamic devices directly, and also you from the aerodynamic department, you have some information that the suspension guys need to know. So make sure that you have maybe a meeting once a week in which you keep in touch with the suspension team, and in which you exchange the informations. And with an intensive exchange, 3 common mistakes can be prevented. One thing is balance is important. I know that sounds quite simple, but most of the time it is better to have a balanced aero than to have more downforce. If you have, for example, if your suspension is rather oversteering, it is not recommendable to have a front heavy aero with a CP near to the front than to the rear axle. So if you have for example, a massive front wing, and you take all the kinetic energy from the air, and your center of pressure is way forward than the perfect balance would be, then your rear just gets loose and it will get slippy, and at some point it will be undrivable. So it might be an advantage if you have less downforce but have balanced it well. So that's a very important point. And the balance of the suspension system, how it is set up, and there are so many parameters that are into that. You only get those informations if you talk with your suspension department. Another common mistake is that you can really have downforce too much, so you can push downforce over a limit. So have a look at the data of your team's tires before pushing downforce to the maximum, because at some point your tires have some kind of saturation area in which the car, in which the tire won't be able to transfer any more side forces, even if the vertical forces are increasing. So what we do with aerodynamics is we increase the vertical forces to push the car and to push the tires more into the ground, and therefore to have more side forces, or to make the tire able to transfer more side forces. And please, if you imagine that you're driving near your maximum velocity of the car, and then there comes a left-hand corner, and now your driver is braking really hard, and due to the mass inertia and the downforce and everything, the front axle will have very, very high tire loads, while the rear axle don't have that high. But the front tires, it can be, if you have too much downforce, that the front tires get in this saturation area and they will just collapse, and they won't transfer any more side forces. Then and then you will have a very understeering car, and the tires will just rub on the street, and your tires will get broken very, very shortly. So make sure that you don't get into this saturation area, and yeah, that is a very, very important point. The last thing about the suspension is the pitch and roll. Make sure that you know the locations of your pitch and roll axles of your car. Your suspension team can give them to you and determine with them your maximum roll angle. Because if you imagine, or if you remember this corner, you're driving into a left-hand corner, then your driver steers in, and the whole car on the right side, or the car rolls over the roll axle, and the right side of your car will get closer to the ground. And if you, for example, designed your front wing to the minimum ground clearance because CFD said, yeah, in this area the front wing operates the best, then I will guarantee you your car won't survive the first left-hand corner, which is driven fastly. In our terms, I think it's like when we have side forces like I think, or side accelerations, lateral accelerations like 2G, then we have like 2 degrees of roll, and that is a very, very massive, very, very massive difference in height from the left-hand side to the right-hand side. And when you consider that your right height is already lower than it is in the static condition due to the downforce, then you have maybe like 15 millimeters ground clearance, and now your car is rolling 2 degrees. Then the front wing will just hit the ground, and yeah, if it's stiff enough, then it will survive, but I don't think it will. So another big thing is that CFD is not the reality. So CFD is based on approximations of the Navier-Stokes equations, which only describe the flow. They don't say what exactly is happening there. And it's a common thinking that what you see in CFD is exactly what happens, and that is wrong. Your geometries, as you saw before from Akram, they are approximated and idealized. And of course you have tolerances in the manufacturing of the car and everything else, and all those aspects, they come together, and the error from the CFD to the reality is growing. And as well, during a CFD simulation, you can make a high number of mistakes which won't have a direct effect on the convergence, but have an even bigger effect on the results. And therefore it is very, 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 very important to validate your results. This is really the essential part of CFD. And I want to show you some validation methods. The most common validation method that everyone knows from watching Formula 1 is the flow visualization, where you just paint a bit of a high viscous paint to the car, and then you drive around and you can see the path of the air on the end plate, for example, here from this Formula 1 rear wing, and there you can see where the air is going. What you can validate with this method is if the flow separates or not, but what you not can validate with this method is how much downforce, for example, your car really produces. Therefore, I will give you something later. Another validation method which is the flow visualization, wow, hard word, method is the wool stripe method, where you just stick all those wool stripes to your car, and it's just the same as with the paint, but it's a bit easier, and yeah, that's something you can really easy do. Another validation method is an analysis of your wheel travel sensors. This picture is from our car. We have those wheel travel sensors mounted to the car, and what you can do here is you can drive with a constant velocity on a long straight, and you do it with aero and one time without aero, and then you can see on the compression of the suspension if there is any vertical force acting to the car. You cannot make a saying about how much downforce you really produce, because there are some suspension kinematics in it and some damper kinematics in it, but you can definitely say that the car is doing around that and that value of downforce. So it's not an exact value, but it can give you a space in which the downforce that your car generates is in. And the last but most simple method is, just driving. Set up a really simple course with maybe like one tight corner, a long straight, and one corner with a big radius, and then let your driver just drive like 25 laps with aero and 25 laps without aero, and do this with 2 or 3 drivers, and then just compare the lap times. And if your aerodynamic devices really are doing what they should do, then I think the lap times with aero should be faster than those without aero. But all those are not the perfect validation method, but if you do some of them, you can move in the right direction. So that are pretty simple validation methods without having to spend time in the wind tunnel. So at this point, I just want to say thank you for the last season to Horsepower Hannover, which was a really nice collaboration. I think we had a daily exchange. Mark, thank you for that, and Henry, I hope we can continue with that. And Prost Hannover. And of course, I also want to thank SimScale for the awesome collaboration, for giving us all the tools, for supporting us every time we had questions, for answering all our questions, and of course for giving me now the opportunity to present our car a bit. And last, thank you to all of you. And as I mentioned before, in case of questions, you can just send me an email if it's not answered at the moment, or if you're watching this later on YouTube and you have any questions, just send me an email to niklas.pfeiffer@em-cologne.de. And that's about my part from the presentation. I hope I could give you some kind of small introduction to the season, and I hope to see you all in Hockenheim, and maybe we can have a talk there and you can show what you did with SimScale. Thank you.
Okay. Hey guys, I just saw that my mic was still muted, so let's do it again. You have not missed a lot. Finally, I would like to present your This Works homework to you. And our aim is to enable you to run your own simulations and leverage SimScale for your own design project. Therefore, this week's homework is about running a simulation of a car you designed on your own. And you don't need to design the full car. Actually, we will provide you with a CAD model of the car we used for the workshop. And your job is to redesign the front wing. And during this homework, you will also get familiar with the process of generating a tessellated STL file as a CAD input. And we have summarized everything you need to know again in a step-by-step tutorial, which will be published tomorrow. You can see like all the steps to create the model. And finally, we have 2 more questions related to Niklas, which I would like to forward to him. So first of question is again by Dietrich, and he wants to know how do you know how much your car is moving and that at a certain velocity with a new aero package before developing and testing it on track?
Well, that's right. That's a limitation. You have to guess. Yeah, not guess, but you have to appreciate a value. We appreciated our CL value in the beginning of the last season to around 2.5, and I think we're at the moment somewhere 2.6 or something. So it's a bit of an realistic appreciation how much your aero is doing. But you can do a roughly calculation of how much downforce your package is generating before simulating. So that is how we do it. But
Yeah.
with the experiences we will gain, yeah, we just appreciate that and guess a bit. But yeah, you cannot I don't know the word, but I hope you got what I mean.
Okay, perfect. There's a next question by Andre Costa, and he asked, Nicholas, you've mentioned that your team is developing your own lap time simulation. Regarding this topic, what kind of aerodynamic simulation do you use to evaluate ride height changes and get important data to your lap time simulator?
Well, I think that goes into the right direction as the previous question, but to add to that, when you're driving around, then you have the wheel travel sensors, and you have an analysis of this wheel travel sensors afterwards. So you can analyze this data and see how much the ride height changes, for example, on an autocross lap in Hockenheim. And then you can just get the value which is most oftenly, and yeah.
All right. Okay, perfect. Nicholas, thank you very much. I think there is one last question left by Iker. What extent does the side force improve the stability of the car in a turn? How many kilograms of side force would be necessary for improving the grip force of the car?
Sorry?
Okay, Iker wants to know what extent does the side force improve the stability of the car in a turn? To what extent does the side force improve the stability of the car in a turn, and how many kilograms of side force would be necessary for improving the grip force of the car?
Well, that's something of a suspension question, but first of all, the side force is used to, if you imagine the car has a mass and the mass has inertia, and when you want to turn in, the car wants to remain on its straight line and don't want to go into the corner, and you have to put side forces to your car to turn it around, and the side forces which you can apply to the car, they are directly dependent from the normal force, so from the downforce that is acting on those tires and the gravity forces of the car. And yeah, I don't think that that these you can measure it in kilogram force, but you have to talk with your suspension guy who has the tire data, and he can give you more information on that. But make sure that you know what you want from him.
All right, Nicholas, thank you very much. Also, thanks to all participants for joining. It was a big pleasure for us to host this workshop series. Don't forget to submit your homework and apply for a SimScale sponsorship. Have a nice week. Hope to see you soon. Bye.
Bye.